All right, so I'm going to do a couple of just application questions with you. I'll confess, sometimes it's tricky to find application questions that exactly relate to your trade. Now, the most application of trig that you're going to use, from what I understand, is when you're working with vectors, which we're going to treat completely separate. So from here on out, we're really doing some trig applications that you will use with electricity. But for today, I just want to look at some basic geometry questions, and I did a little research about some issues that come up that they have to work on some trig with. There's things that I'll admit you probably are right if you were to say that an engineer will usually solve these issues for you, and you're just doing maintenance. It's not so much your concern, but sometimes just being able to converse with the engineer on the site, or you never know where you're going to end up. You may end up coming back and or going further and continuing your education, and maybe you do end up taking that engineering route and you end up working on the design team. Those kinds of things help just build skills. So sometimes it is about being able to talk intelligently with the people that are around you. So I'll admit, and I'm a little bit grasping at straws here, because sometimes there's outcomes that they say, well, they need to know how to do the basics of them, but they don't always give me all the specifics. So you'll have to bear with me a little bit if the applications don't feel as real as they could be. I'll try my best. As I'm terrified of heights, I've never been at the top of a turbine, let alone attempting to do any maintenance on one. So you'll have to forgive me a little bit if we're working at stretching to get some application out of it. So the first question we're going to look at is a question that just pertains to surveying. So this is one of the scenarios where trig is really important, is when people are doing site surveying. If you're working in a new build area, guaranteed you're going to have some site surveyors on hand. So this is the kind of math that they would have to worry about. Maybe not this particular question, because hopefully if you're installing turbines, you know how tall the turbine is. But sometimes to know what's the overall height or what's the elevation can be the thing you'll want to end up figuring out. But this is, I could find a good picture for it. I'll confess the picture is stolen goods, but we're under the 10% for copyright, and the original individual didn't give me any kind of reference for where the picture originally came from, so it's been stolen at least twice. So here's my confession for the day. So if a mountain is half a mile from town and the altitude of the mountain is 1,200 feet higher than the town, and the angle of elevation from the town to the top of the turbine is 29 degrees, how tall is the turbine tower? So this is, and the question, the triangle has already been drawn in this particular question. So this is a question where angle of elevation is really, if you were looking upwards, what the angle is that you would basically have to tip your eyes or lift your eye, tip your head or lift your eyes in order to see an object that's higher. Angle of depression is when we look downwards. So elevation is looking upwards, depression is when we look downwards. Sometimes those words come up in questions, and if it comes up, you know what it means. So we want to find out how tall is the tower. Well, we know the height of the mountain. That's already labeled in the diagram for us. You'll notice that the half mile has been converted into feet. That's important because we have to use matching units when we do trig ratios. So you can't put half a mile with feet. If the units don't match, you won't get the ratio right. So trig ratios always need the same unit top and bottom with that opposite and adjacent or hypotenuse, whichever one you happen to be using. So if we can find out what is the total height, including the height of the mountain, we can figure out what is the height of just the turbine. So in this particular case, here's our angle, and the side that includes the turbine is opposite our angle. So I'm just going to label it as O rather than giving us two X's. So if we can figure out side O, we can solve this problem easy. This side happens to be our adjacent side, because it is next to the 29. So let's figure out which ratio do we use. we are going to use the ratio that involves tan because we have the adjacent and we want to know what the opposite is. You will find you use the tan ratio probably more than most others. I find the tan ratio is the one that seems to be used the most common. So the tan of our angle is equal to opposite over adjacent. So the tan of 29 degrees is equal to opposite over adjacent, and if we put the adjacent in feet, we're going to get feet out. The unit for the top and the bottom always has to match. Rearranging it, opposite is equal to 2,640 times the tan of 29 degrees. Now, my calculator is very easy to put this all in one go at it. That's a great way to avoid having to worry about rounding. If you do need to round your 29 degrees, tan of 29 gives you 0.5543. Keep all of those, keep at least 4 decimals, okay? I'll put it in just in case you're wondering or you're having a calculator issue. 0.5543. You want to keep at least that many decimals. And the opposite side happens to be 1,463.4 meters. Or sorry, not meters, we're in feet. What did I just say about units? Okay, so that's the total height. 1,463.4 feet. Now, if we want to know just the turbine, we are going to take our number, 1,463.4, and subtract the height of the mountain. So it just makes it a two-step question. It's a little more complicated version of the simple triangles that you've had. And we find that our turbine is 263.4 feet tall. So nice, easy question. Just making sure that you use common units is kind of the most important thing there. So nice and simple, but the trade application from that is if you're dealing with somebody doing a survey. This is a question I really like because it can relate. We'll do a question that kind of relates to this in physics. So we're going to get a sneak peek now of just some of the background math that you have to worry about. So a V52, and these are specs that I Googled and found, so they're real diameters and real heights. So a V52 has a hub height of 57 meters and a rotor diameter of 52 meters. What's the height of the blade at point E and point B? So what I want to know the tip height. I want to know how far off the ground is that tip? And if the blade was up here at point B, how far off the ground are we? All right, so this is really what we're looking for, is what's this height? And then for B, we'll do the same thing. Now I'm going to start with E because E is just a little simpler spot to see. There's some less numbers around. So let's label our diagram. We know that the hub height happens to be 57 meters. That's going to be important for us. And if we know the rotor diameter is 52 meters, the radius, this takes us back to our previous units, is equal to 52 meters divided by 2, which gives us a diameter. Did I actually think I did that? Of 26, yes. I was just looking at it, I didn't see the number that I wanted really quickly. I just didn't label it. So our radius is 26 meters. So the length of our blade, or from the center of our hub to the tip of our blade, this length here is 26 meters. So now we need to find a triangle because right now it just looks like circles. The hub height point, point D, is basically our 0 point. We're going to treat that as a 0. If we can find out how far down point E is, we can figure out, well, what's the distance to the ground, because we can just subtract that from our hub height. So we're going to want to figure out, I'm going to see if I can switch colors here. Maybe I can switch to, hopefully this blue shows up okay. So if we can figure out what is this measurement, we will be able to solve what is the height from the ground. Well, if we look, we have a triangle. We have the triangle with a hypotenuse. So this is there's our right angle here. We have a hypotenuse that's equal to the length of our blade, or half of our, we'll call it a rotor radius. I don't know if that's actually a word. Rotor diameter is a word, so rotor radius should be, I guess. So our hypotenuse is going to be 26 meters. We don't know what our height is, but we do know that this angle is 30 degrees, so it's dropped 30 degrees in its circle. So it's actually pretty easy for us to calculate. We need a ratio that uses hypotenuse, and x is the opposite side. Which ratio uses opposite and hypotenuse? Well, we need sine. So the sine of an angle is equal to opposite over hypotenuse, so we'll put in some information. Our angle is a 30-degree drop, so we'll put in our 30. We want to know what's the opposite side, so what's the distance down from horizontal that it's moved, divided by our hypotenuse, which is our blade length, or our rotor radius, which is 26 meters. Solving this is very easy. Rearranging. It's O divided by 26, so we're going to multiply by 26. O is equal to 26 times the sine of 30, which gives us a total of 13 meters. Okay, so that's not the height though. That's not the height at E. So if we want to go a little further, the height at E is equal to our hub height, which is 57, minus how far down that blade tip has turned, and it's dropped 13 meters, which gives us a height of 44 meters from the ground. So the 13 meters is 13 meters below hub. And then if we want to know the height, that's what we do. Let's section this off. I'll switch colors and we'll figure out what it is at B. So B is basically the same math. We'll do that one in green. So the height at point B. So if the blade was turned to point B, here's our height. Again, it's going to be our opposite side. The angle, we have 30 degrees here and 30 degrees here. So this is going to give us a total of 60. So we have basically, if I was going to re-sketch it, we have a new triangle. It's a 60-degree corner there. I need to know what's that height, because this is how much above the hub, the height above the hub that we are. And then again, we have a rotor radius of 26 meters. So it's exactly the same formula. Our x is still our opposite. So it's, again, we're going to use the sine ratio. So the sine of 60 is equal to opposite over 26. So 26 times the sine of 60 equals, and if you're calculating that, we're going to get 25.5. And if you want to know the height, well, we go to the hub height, plus we go above it, 25.5 meters, because that triangle sits above the hub, which gives us a total height of 79.5 meters. A physics question that I could give that would make you calculate this is, you could say a blade that was 60 degrees above horizontal has a piece of ice shed. How long does it take to fall? If we were talking projectiles, we'll say how long does it take to fall and how far does it fall? So those are the kinds of scenarios that we can use in order to figure out some of our physics questions. So I call that an applied question because we kind of have to think about it in a real world context. If you're looking at angles that are above here, we have to add the height to our hub height. If we're on the bottom half of horizontal, we're going to subtract from our hub height. Another question, this is a question that's kind of an engineer related question, I guess. I found this interesting. I don't know if any of you ever travel between PEI, just right where you transition from Nova Scotia to New Brunswick, there is I don't know if it's all called the Tantramar Marsh, but it's in that rough area. There's an area there that's got a little causeway, but there's a whole pile of turbines. It's a really open marsh area. One of the reasons for putting turbines there, as I'm sure you already know, is when you have open flat areas, we don't have to deal with surface roughness factors, where basically, the wind's not going to get slowed down due to the roughness of the terrain. So it's one of the reasons why it's great to have them even out in the water, although that presents a whole new pile of complications. But at that particular area, if you're driving through and you're listening to the radio, you're going to find the signal gets terrible. Now, I don't know if it's all due to the turbines, because I know the turbines, it was always not a great spot, but I think it's gotten worse over the years since more turbines were added in that area. So there's a nice little area where there's wind turbines. Now, what can happen is when you have like a radar signal or a radio signal, radar signals I think are more susceptible, and it's actually really cool. The Environment Canada website shows wind farms as blips on their radar that look like weather patterns, and it's not. The blades rotating causes the radar signal to bounce back more rapidly than it should. And what it does is it looks like there's something there, but it's caused by the rotation of the blades, because the position's changing, bouncing back irregular signals makes the radar think that there's something there and it's not a stationary object, which is kind of cool. So it's something they have to think about. If you were putting a wind farm somewhere, you probably want to think about how close is the airport. Airports are great flat areas. I'm sure it'd be a great spot, as long as there's enough clearance, of course. But if it interferes with radar signals, it could potentially cause issues. So anyway, I found a couple of interesting articles about that and had a little nerd out session on it. So this picture is just a really simple picture, and it gives us a really good question to solve, and just to make us think in a little bit different way. So we've got 3 turbines. They're positioned each 170 meters apart. So put them as close together as possible instead of spread apart. A radar signal is emitted 1 kilometer away. Over how many degrees are the shadow zones situated? So what happens is the areas behind these turbines, it screws up the radio frequency or the radar frequency behind them, so you don't always get clear signals. So I don't know if that's what happens at that area in Nova Scotia, right on the border there, where the radio signal gets really crappy. I don't know if it's what's considered to be a shadow zone or if there's some other factors coming into play. If one of you guys happens to work there on OJT, maybe you can find out for me. That'll be some interesting questions. Is that something that they had to worry about, or is it just interference from the large number of radio towers that are also in that area? So to do this question, we need to find a right triangle. Right now, we have a triangle there. So if we take this and we connect these 3 turbines, we have a triangle. I know the picture, they're not quite perfectly in a straight line. We're going to assume they are. They're very close to it. We don't have a right triangle because, well, we've got different angles, but it says the 3 turbines are each 170 meters apart. So they're equal spacing. So we can break apart, go down the middle, break this triangle into 2. Lost my pen here for a sec. I think it's just that it's not red. Put it back to our red color. And we know that there's 170 meters here. We know that this radar signal, this distance here, happens to be 1 kilometer or 1,000 meters. And we need to figure out, well, if we can figure out what the angle is on this side, it should be double because they're each 170 meters away. So we've got 170 meters here as well. All right. So if we know the angle for one triangle, we can figure out what's the entire angle. So we're just taking a simple triangle that's not a right angle. And we're saying, can we break it into a right angle triangle? Here's our picture. It's easier to see when it's big. We got 1,000 meters, 170 meters, and what's our angle? You will notice we have adjacent and opposite. Tan is TOA, TOA, so it uses adjacent and opposite. So the tangent of the angle that we're looking for, and this angle is only going to be half, is equal to 170 over 1,000. So our angle is equal to inverse tan of 0.170, which gives us 9.6 degrees. Now, depending on whether you round before you double it or whether you don't, can change the degrees slightly. So the total angle, this total angle through which there's going to be shadow zones, would be our angle 9.6 times 2 leaves us with 19.2 degrees. So this angle here, the whole thing is 19.2 degrees. So that means as we expand out, we can figure out, well, how far, over what distance would you expect to see shadowing or irregular patterns, because that angle will be the same no matter how far out we go. And eventually you'd get to an area where the shadow should stop and it should be negligible. One last question. Jeff will like this question because we're going to level something. We're going to level it with Trig. I don't know if you have digital levels. Digital levels, I think it's kind of cool. But you have to be good at math in order to use them because it tells you how much it's off level. But then you have to be able to figure out, well, what's the measurement in order to make it level, as opposed to just looking for where's your bubble in the middle. But anyway, I think this is a good question. If you don't think it's a good question, that's okay, but I think it's a good question. So we have a rod that's 245 millimeters. Okay. Now this is a little bit more accurate way to figure out what exactly you'd have to shim. We want to know, okay, how much do I have to raise here? How much does this end have to go up in order for it to be level on this black line? Well, our inclinometer, or our digital level, says that we're 5.75 degrees off of level. So this angle is 5.75 degrees. The height that I need to adjust it is the measurement over on the right-hand side. So let's figure out our sides. Well, here's my right angle. My right angle is with level and vertical. So there's my right angle. So this side must be my hypotenuse, and then this side is our opposite. So SOH, sine, uses opposite and hypotenuse. So the sine of our angle is opposite over h. Plugging in our number, the sine of 5.75 equals x over 245. Excuse me. X is equal to 245 millimeters times the sine of 5.75 degrees. Plugging that into our calculator, we get 24.5 millimeters. And if you remember back from earlier when you did conversions, that is also equal to 1 inch. I didn't ask you to do the conversion. I randomly picked those numbers. They were not planned, but I thought it quite interesting that we ended up with exactly 1 inch is what we would need to raise the right-hand side of the rod in order to bring it up to level. And that finishes off this particular section, and you'll have just a short assignment in order to hand it to me.